Welcome to day 12 of the advent of compiler optimization. Today we're going to continue looking at loops, and we're going to start by looking at the accumulate sum kind of routine that we looked at a few days back. So here's the code. It's taking a span of integers, which if you remember is essentially just a pointer and a count of integers. And we are initializing with 0, and then we're looping over using range fors, which we discovered are actually the best way of looping. And then we're returning the count. And again, standard accumulate is a much better way of doing this, but we're going to experiment with it and see what other tricks the compiler has up its sleeve. I've chosen to use ARM v7 today, partly for old time's sake, but also because it stops some of the more complicated optimizations that happen when we have vector instructions available. And we will talk about those later, but for today, I'm looking at simpler code generation to make things easier for us. So, what if we change our sum routine to make it a sum, optionally, of sum of squares? So, squared. So this is going to be a flag that tells the function that we want to actually sum the squares of the integers rather than just the integers themselves. Now, this is not a good way of doing this, but you might reasonably go, okay, let's say squared query value times value, value else value. So if the routine has been asked to sum the squares, we use value squared, else we use value. Pretty straightforward. Let's have a look at what happened in the assembly code on the other side. So starting from the top, we're doing our usual comparison and return if the number of elements is 0. So with the ARM v7, every instruction can be conditional. So we see that if R1, the number of elements is 0, then we set the return value to 0, and then we return. BXEQ is essentially a return instruction, or BXEQ to the link register anyway. Then we push some registers that we're using. We are multiplying the size by 4 because presumably we're going to walk a pointer along the array. And we're going to be walking along the array. We use the link register for a temporary value, and we're setting our 0 to 0. That is going to be presumably our sum. And then we're into our loop. We read a value. We say, is the bool that we were passed in, is squared true or false? We make R3 equal to R12. Now, R12, if we track back up here, is the value we've just read. So R3 is now value, as is R12. So both R3 and R12 are value. And then we move if equal 1 into R3. What does this mean? This means that R3 is either value, or if the Boolean we passed in was 0, then it is 1. So we've got either a 1 or the value. We then decrement the number of things that we're going to be bytes that we're processing, and then we see this MLA instruction, which is a pretty neat trick that the compiler has pulled. MLA is a multiply and add instruction. It combines both the multiply and the addition. And what this is R0 is equal to R3 times R12 plus R0. So effectively, we're doing total plus equals R3, which is, as you know, either value or 1, and R12, which is the value. So we're either multiplying by 1 or we're multiplying value by itself. That's a really neat trick for taking away a conditional and a big jump around whether it's adding or multiplying. I think you'll agree that's a neat trick that the compiler has pulled. However, it does sort of make you wonder, what if this multiply and add instruction was relatively expensive? Then we're sort of paying the cost of always doing a multiply and add, even when we're not squaring the values. We're always multiplying by 1, and maybe that's expensive still, who knows? The compiler also knows this and can deal with it, and in fact if we put the O value, the optimization value, up to 3, we'll see that the compiler has a completely different approach. Starting again from the top, we see the branch if the number of count was 0, and then we do some of the other sort of setup code for various loop counters and accumulators. And then we compare whether or not the squared value was true or false. And if it was false, if it was equal to 0, 0 and 1 is obviously what a Boolean boils down to, then we're going to LBBO underscore 4. Otherwise, we fall through into LBBO 02 here. In the LBBO2 loop, we can see that it's reading a value and it's multiplying and adding it unconditionally every time. and then it returns. So if the squared boolean was not false, it must have been true, then we have this loop here that is just doing the squaring and adding. Otherwise, we've jumped over to LBBO_4, and that loop just does the add. So behind the scenes, the compiler has rewritten our code, and it has checked the squared value outside of the loop, and then duplicated the loop, once doing the square, and once just doing the add. It's as if we'd written this code. If squared, and my dog is probably going to bark because the postman's just arrived, else, gosh, he did not. He knows I'm recording, that's nice of him. We're going to say, so if squared, we're going to say value times value, otherwise squared sum plus equals value. And let me just reformat all of that. So you'll see that the code now is exactly the same as the compiler had generated. And in fact, if we go back down to O2 now, we'll see that the output is in fact exactly the same. Maybe the reason the compiler doesn't do this by default is that by duplicating that inner loop, we're actually increasing the amount of code that's being generated, and that might be a problem, and it might be put more pressure on the instruction cache and other things like that. So only when we put on O3, which does typically blow up the code size in order to get more efficiency out of the system, do we see this kind of trick. This trick that the compiler is doing, where it moves a constant out of the loop and sort of duplicates the body of the loop given that the constant is true or false or different values of that constant, is called loop unswitching, and it's one of the many things the compiler applies for us behind the scenes and makes our code more efficient. Loop unswitching is just one of the many optimizations the compiler can pull for loops. We'll continue looking at those over the next few days. I hope to see you tomorrow.